What if a knock on the door came not from your neighbor, not from down the street, but from across the galactic expanse, from a time before our own world was even born? What if that knock wasn't a sound, but a sudden, inexplicable flash of light in the dark? On October 29, 2025, humanity received such a knock. An ancient visitor, a traveler of the interstellar void known as 3IATLAS, did something so profoundly strange, so utterly contrary to our expectations, that it sent a shockwave through the entire scientific community. This isn't just a story about a comet. This is a story about a mystery that challenges the very foundations of what we think we know about the universe and our place within it. What astronomers are uncovering right now, in the data streaming back from our most advanced telescopes, is forcing them to ask questions they never dreamed they'd have to consider. Forget what you know about shooting stars and icy wanderers. This is something else, and the story is still unfolding, right now, as we speak. Imagine a control room bathed in the cool, sterile glow of computer monitors. For weeks, astronomers Chi-Chung Jung from the prestigious Lowell Observatory and Carl Battams at the U.S. Naval Research Laboratory had been tracking 3IATLAS with the focused patience that their profession demands. This was, after all, only the third confirmed interstellar object ever detected. Every photon of light it emitted was a precious jewel of data from another star system. They had their models, their predictions, their elegant equations that described how a comet should behave. As it skimmed past our sun, a point in its journey we call perihelion, they expected it to brighten. Of course it would. The sun's immense heat would act like a cosmic blowtorch, vaporizing the ices on its surface, causing it to glow more intensely. They anticipated a gradual, predictable curve on their graphs. A gentle crescendo of light. What they got was a cataclysm. On October 29th, the data didn't just curve upwards, it shot upwards like a rocket. The brightness of 3IATLAS exploded, surging at a rate twice as fast as it had been just moments before. The graceful crescendo became a deafening blast. In observatories around the world, automated alerts would have begun screaming. Phones would have started ringing in the dead of night. This wasn't just an anomaly, it was a violation of the rules. Think of it like putting a pot of water on the stove. You expect it to heat up slowly, then simmer, then boil. You don't expect it to sit there placidly, and then instantly flash into a superheated cloud of steam. Jang and Battams, staring at their screens, had no immediate explanation. Their meticulously crafted models were shattered in an instant. This object, a silent wanderer that had journeyed for what could be 7.5 billion years through the unimaginable cold and dark of deep space, had just woken up, and it had woken up screaming. This single event forces us to confront a profound reality. We often live our lives with a sense of certainty, believing we understand the rules that govern our world, our relationships, our future. We build models and plans based on past experiences. But every now and then, life throws a variable into the equation that we never saw coming. An unexpected event, a sudden change, that shatters our predictions. 3IATLAS's outburst is a cosmic-scale reminder of this truth. It teaches us that the universe is not always the tidy, predictable place our science textbooks describe. It is wild, chaotic, and filled with genuine surprises. The lesson here, applicable to our own lives, is the importance of intellectual humility. It's the ability to see our most cherished beliefs and models fail, and instead of despairing, to look at the new data with wide-eyed wonder and ask, okay, what does this mean? That is the very soul of discovery. It's what Jung and Battams were doing in that moment, not just observing a comet, but staring into the face of a profound unknown. As the initial shock of the outburst began to subside, the real detective work began. Scientists around the globe scrambled to dissect every scrap of data, and what they found only deepened the mystery. The first clue came from the light itself. Using spectrographs, instruments that act like cosmic prisms, breaking light down into its constituent colors, they analyzed the comet's glow. The result was bizarre. The spectrum of 3I-ATLAS had become bluer than the light of our own sun. This blue shift is a specific chemical fingerprint, a neon sign flashing across the solar system, telling us that a furious chemical reaction was underway. It pointed to the presence of C2, or diatomic carbon, and imidazine compounds, NH2. These are the spectral signatures of ice turning directly into gas, a process called sublimation, but the intensity was off the charts. Then came the radio observations, which provided a measure of something even more fundamental: water. In the 2 weeks leading up to its solar flyby, 3I-ATLAS was shedding an astonishing 5.7 times 10 to the 28th power of water molecules every single second. To put that number in perspective, that's like draining more than 400,000 Olympic-sized swimming pools into space every minute. It was 40 times more water than it had been losing just a month earlier. One scientist, struggling for an analogy, described it as a fire hose on full blast. It was a torrent, a cosmic hemorrhage of water vapor pouring out from this ancient object. But here's where it gets truly unsettling. Our space-based observatories, the SOHO and Stereo A satellites, along with the new GOES-19, are equipped with special instruments called coronagraphs. These create artificial eclipses, blocking out the sun's overwhelming glare so we can see faint objects close to it. When they turned their eyes to 3I-ATLAS, they saw something that defied all convention. They saw the glow, the bright, elongated spot of gas, but they saw no dust tail. None. A comet's tail, that beautiful, iconic plume of dust and debris, is supposed to be the inevitable consequence of such a violent outgassing. The escaping gas should have been dragging trillions of tiny dust particles with it, creating a spectacular trail, but there was nothing. It was like seeing a massive fire without any smoke. This single observation was a paradox. Where was the shrapnel from this explosion? How could you have a fire hose of gas without kicking up any dust? It meant the very composition of this object was unlike anything we had ever encountered. It was as if this visitor was made of pure, solidified gas, with almost no rock or solid matter mixed in, a composition that our theories of comet formation struggle to explain. This brings us to a crucial point about perception in our own lives. We are conditioned to see patterns. Fire means smoke. Rain means clouds. A smile means happiness. We rely on these associations to navigate our world. But what happens when we encounter a fire with no smoke? What happens when the expected consequence of an action doesn't materialize? 3I-ATLAS's missing tail is a powerful metaphor for these moments of cognitive dissonance. It challenges us to look beyond our assumptions and question the very links we take for granted. It's a call to investigate the underlying reality rather than just the surface appearance. When something in your life doesn't add up, when the story you're being told doesn't match the evidence you see, that is your moment to become a scientist. That is your moment to ask, where is the dust tail? It's a question that can lead to uncomfortable truths, but it is always the first step toward genuine understanding. To get a closer look, astronomers turned to our most powerful tool, the James Webb Space Telescope. What JWST found didn't solve the mystery, but it added a profound and unexpected layer of history to our visitor. Using its near-infrared spectrograph, Webb analyzed the comet's chemical makeup and confirmed what some had suspected. It was unusually rich in carbon dioxide. But it was the analysis of its physical structure that provided a true paradigm shift. The data revealed that 3I-ATLAS is wrapped in what scientists are now calling a deep irradiated crust. This isn't just a surface layer. It's a fundamental transformation of the object's very being, forged over billions of years. To understand this, You have to imagine the environment of interstellar space. Here in our solar system, we live inside a protective bubble called the heliosphere, a magnetic field generated by our Sun that deflects the most energetic particles from the galaxy. Out there, in the dark between the stars, there is no such shield. Objects are relentlessly bombarded by galactic cosmic rays, high-energy particles hurled across space by supernovae and other cataclysmic events. A team led by Roma Maggiolo from the Royal Belgian Institute for Space Astronomy ran computer simulations to model what this constant, eons-long bombardment would do to a comet. Their findings were stunning. The cosmic rays would penetrate deep into the nucleus, about 50 to 65 feet, fundamentally altering its chemistry and physics. Carbon monoxide would be converted to carbon dioxide. The crystalline structure of the ice would be shattered and reformed. The material would be cooked, compressed, and hardened by radiation until it no longer resembled the pristine ice from which it was born. This discovery is a game-changer. Scientists had hoped that interstellar visitors would be like time capsules, giving us a pure, untouched sample of the chemical conditions around another star. But Maggiolo's research suggests this is not the case. What we are seeing on the outside of 3IATLAS is not a sample of its home system. We are seeing a relic of its journey. As Maggiolo himself powerfully stated, the object is now more a product of its interstellar journey rather than where it came from. It is wearing a suit of armor, forged by the very harshness of the void it traveled through. This raises a tantalizing and almost philosophical question. What's underneath? Beneath that 60-foot-thick shell of radiation-processed material, does the original, pristine ice from its birth 7.5 billion years ago still exist? Is the Sun's recent outburst the first step in stripping away that armor to reveal the heart of the traveler? This concept of a journey fundamentally changing the traveler is one of the most powerful metaphors for the human experience. None of us arrive at our present moment as pristine, untouched beings. We are all shaped, hardened, and transformed by the cosmic rays of our own lives, by our struggles, our triumphs, our losses, and our loves. We all develop an irradiated crust, a protective shell of experience, personality, and defense mechanisms. But this shell is not our true origin. Beneath it lies the core of who we are. The story of 3IATLAS reminds us that to truly understand someone or even ourselves, we cannot simply look at the surface. We must appreciate the journey that created that surface. And it offers a hopeful possibility that under the right conditions, with the right catalyst, like the sun's heat, that crust can be peeled back, revealing the pristine core that has been preserved all along. It's a profound lesson in empathy and self-discovery, written across the cosmos. With each new piece of data, the enigma of 3IATLAS grew, and so did the unease in some corners of the scientific community. This is where Professor Avi Loeb enters the story. The former chair of Harvard's astronomy department, Loeb has become one of the most prominent and controversial figures in the search for extraterrestrial intelligence. He was the leading voice who argued that Oumuamua, our first interstellar visitor in 2017, displayed characteristics that were not easily explained by natural phenomena. Now, with 3IATLAS behaving so erratically, Loeb has made a bold and public move. He has formally requested that NASA release all of its scientific data on the object to the public. His argument is simple and, for many, deeply compelling. This is not just another comet. This is an object of extraordinary scientific and potentially historical importance. The data collected by NASA's fleet of instruments, the Swift Telescope, SOHO, Stereo, GOES-19, represents a priceless, irreplaceable treasure trove of information about the interstellar environment. Loeb argues that this data should not be siloed within NASA or shared only among a select few research groups. It should be available to everyone, to any scientist, any university, any citizen researcher around the world who has the skill and the desire to analyze it. This, he contends, is how science should work. Openness and transparency lead to better results, as more eyes on the data mean a higher chance of spotting something that was missed. But beneath this principled stand for open science, there is a powerful, unspoken question that hangs in the air. What exactly is in that data? Why the urgent call for release now? Is it possible that NASA's instruments have detected something even stranger than what has been publicly discussed? Are there measurements, spectra, or behavioral patterns that do not fit neatly into a press release? Loeb's request is not just a call for transparency. It's an insinuation that there may be more to this story. He is, in essence, asking if the official narrative is the complete one. This transforms the story from a purely scientific mystery into one with elements of intrigue. It pits the institutional caution of a major space agency against the relentless curiosity of one of its most outspoken critics. The parallel to our own society is impossible to ignore. In every field, from government to medicine to corporate finance, we grapple with the tension between secrecy and transparency. Data is power, and those who hold it often control the narrative. Loeb's call is a microcosm of a larger societal struggle for open access to information. It reminds us that progress, whether in science or democracy, often depends on the courage to demand the full story. It encourages us to be critical consumers of information, to ask what data we aren't seeing, and to champion the principle that knowledge, especially knowledge that belongs to all of humanity, should be free. What do you think? Should all scientific data collected by public agencies like NASA be made immediately and freely available to the public, no matter how strange or unsettling it might be? Just as the mystery of 3IATLAS's behavior deepened, a radical new theory emerged that threatened to change its entire context. Professor Susanne Falsner, a researcher at the Forschungszentrum Jülich in Germany, has proposed something extraordinary about objects like this. She suggests they might not be cosmic debris at all. They might be the seeds of planets. This idea addresses one of the most persistent problems in planetary science. We know that planets form through accretion, where tiny dust particles in a disk around a young star stick together to form pebbles, then rocks, then boulders, and so on. The problem is, our computer simulations consistently show that once these objects grow to about a meter in size, they should stop sticking. The chaotic, high-speed environment of the protoplanetary disk should cause them to shatter upon collision, not merge. It's a critical gap in our understanding. How do we get from meter-sized rocks to planet-sized worlds? Falsner's answer is elegant and profound. Maybe we don't. Maybe, she suggests, the process gets a massive head start. Her models show that as a young star system forms, its gravitational field could capture millions of interstellar objects like 3IATLAS that are just drifting through the galaxy. These objects, already hundreds of meters or even kilometers in size, are large enough to bypass the meter-sized barrier completely. Once captured, they would serve as gravitational anchors, ready-made nuclei that could rapidly attract the gas and dust around them, and begin the planet-building process in earnest. Interstellar space, in this view, is not just an empty void. It is a galactic nursery delivering the fundamental building blocks for the next generation of planets. This theory is particularly powerful because it explains another long-standing observation: why massive stars, which have very short-lived planet-forming disks of only a few million years, are often found to have giant planets like Jupiter. Traditional theories struggle to explain how a gas giant could form so quickly. But if the system was seeded with large interstellar objects from the beginning, the process would be dramatically accelerated. When we look at 3IATLAS through this lens, its identity transforms. It ceases to be just a comet. It becomes a potential world that never was. It is a building block of a planet that, for whatever reason, was never captured by a young star. It was left to wander the darkness alone, a cosmic orphan carrying the blueprint for a world within its icy heart. This idea recasts the entire narrative, filling the cold, empty void between stars with a sense of potential and interconnectedness. It suggests that the very stuff of our world may have originated in another, long-dead solar system, delivered here on a journey across the stars. It makes the galaxy feel less like a collection of isolated islands and more like a single, vast ecosystem. The physical statistics of 3IATLAS are as mind-boggling as its behavior. Current estimates place its age at around 7.5 billion years old. Let that number sink in. Our entire solar system, including the Sun and the Earth itself, is only about 4.5 billion years old. This object existed for 3 billion years before our planet was even a glimmer in the cosmos. It was already a seasoned traveler of the galaxy before the first hint of life emerged on Earth. It has witnessed a sweep of cosmic history that we can barely imagine, a time when the Milky Way itself looked fundamentally different. And its journey reflects this ancient origin. It is moving at a blistering speed of over 130,000 miles per hour relative to our solar system. But it's not just the speed, it's the trajectory. Observers have described its path as unusually flat and straight. Comets from our own solar system have been tossed and turned by the gravity of Jupiter and other planets for billions of years. Their orbits are often elliptical, tilted, and chaotic. 3IATLAS's path, by contrast, is a clean, unwavering line. It screams with every mile it travels. I am not from around here. I am just passing through. It is the trajectory of a true interstellar tourist, unburdened by the gravitational politics of our local neighborhood. What has this object seen on its 7.5 billion-year odyssey? What stellar systems did it drift past in the darkness, never quite close enough to be captured, but close enough to be bathed in the light of alien suns? It came from somewhere in the galactic frontier, but we will likely never know its true home. The star it once orbited may have died billions of years ago, swelling into a red giant and then collapsing into a white dwarf, all while its lost child wandered on through the void. This object is not just a piece of rock and ice. It is a witness. It is a silent historian carrying the memory of a past so deep it predates our own existence. Its presence in our sky is a humbling reminder of our own temporal smallness. We are a fleeting moment, a brief spark of consciousness on a young planet. And for a few short months, our timeline has intersected with a traveler from the dawn of the galaxy. It's an encounter that should fill us with a profound sense of awe, a feeling we can tap into in our own lives by simply looking up at the night sky and trying to comprehend the sheer scale and age of what lies beyond our world. As you might imagine, the scientific community is now fiercely divided over how to interpret this cascade of anomalies. The debate has split into two main camps, each with a compelling, yet incomplete, explanation. On one side, you have the pragmatists, the scientists who are comfortable with the explanation that 3IATLAS is simply a natural comet, albeit a very, very weird one. They argue that its unusual composition, a direct result of its formation in a different stellar system and its long radiation-filled journey, is enough to explain its strange behavior. Their key hypothesis for the explosive brightening is the threshold effect. They propose that the comet's nucleus was initially coated in a protective layer of frozen carbon dioxide. As it got closer to the Sun, this CO2 gas began to sublimate, but it also had a cooling effect on the surface, acting like a temporary shield that prevented the far more volatile water ice underneath from vaporizing. But at a specific distance, a critical temperature was reached. The CO2 shield depleted all at once, and the raw, pristine water ice below was suddenly and violently exposed to the full, direct fury of the Sun. The result was the explosive, fire hose-like outgassing we observed. It's a plausible, elegant explanation that fits within the known laws of physics. But on the other side, there are the skeptics, the researchers who remain deeply unsettled. They point to the sheer number of coincidences and anomalies that have to be explained away. The explosive brightening that doesn't match any existing model. The complete and utter lack of a dust tail. The perfectly flat, arrow-like trajectory. And most naggingly, the timing. Why did the outburst happen almost exactly at perihelion, its closest point to the Sun? Natural processes are typically messy and gradual. A sudden, precise, threshold-like event feels tidy. It feels almost engineered. These scientists aren't jumping to conclusions. They are not saying, "It's aliens," but they are asking, quietly in research papers and more loudly at conferences, what else could explain these observations? They are arguing that when your data consistently deviates from your model, you either need a better model or you need to consider that you're looking at something fundamentally different from what you assumed. This debate is science at its best. It's a clash of ideas, a rigorous testing of hypotheses driven by baffling data, and it offers a powerful lesson for how we should approach complex problems in our own lives. We are often presented with two choices: accept the simple, comfortable explanation, or embrace the discomfort of uncertainty and ask harder questions. The story of 3IATLAS teaches us that it's okay to live in that uncomfortable space. It is not unscientific to acknowledge that our current explanations are insufficient. In fact, that acknowledgement is the very starting point of all great discoveries. The moment we say, "I don't know," and the standard answer doesn't feel right, is the moment we open the door to a deeper truth. Let's step back and look at the complete profile of this object, because when you assemble all the pieces, the picture becomes even more intriguing. First, its mass. Early estimates suggest 3IATLAS weighs in at a colossal 33 billion tons. For comparison, Halley's Comet, one of the most famous and massive comets in our history, is about 22 billion tons. So our visitor is significantly more massive, a true behemoth of the interstellar void. Mass alone isn't proof of anything, but it adds to its imposing presence. Then there is its durability. As we've discussed, the James Webb Telescope revealed its 50 to 65-foot thick irradiated crust. This shell, forged by billions of years of cosmic ray impacts, isn't just a surface feature. It's a suit of armor. It would make the object incredibly resilient, protecting the interior from further radiation damage and maintaining its structural integrity against micrometeorite impacts. In a very real sense, the brutal journey itself made 3IATLAS stronger and more durable. Now, let's engage in a thought experiment. If you, as an incredibly advanced engineer, were tasked with designing a probe to travel between stars for billions of years, what would its key features be? First, you would need extreme durability and protection from the harsh radiation of interstellar space. An irradiated crust, perhaps even one that forms naturally over time, would be a perfect solution. Second, you would want it to be passive for the vast majority of its journey, not requiring active power or maintenance for millennia. Third, you would need some kind of mechanism to wake it up or have it perform an action when it reached a target environment, like a star system. This would likely be a threshold-triggered system, designed to activate when solar radiation reached a certain intensity. Now, look at the observed characteristics of 3IATLAS. It's ancient, it's massive, it has a protective crust, and it exhibited a sudden, threshold-triggered burst of activity right at its closest approach to a star. The properties we observe are eerily consistent with the properties you would expect from a designed object meant to travel between the stars. Now let me be absolutely clear. This does not prove anything. It is not evidence. It is merely a compelling and, for some, unsettling parallel. But it highlights why the scientific method is so crucial. We must not start with a conclusion. We must gather data, test hypotheses, and look for ways to distinguish between competing explanations. The hypothesis that 3IATLAS is a natural object is still the most likely, but the hypothesis that its characteristics are also consistent with an artificial object is, at this point, not zero. And that fact alone is what makes this moment in history so electrifying. It forces us to be thorough, to be rigorous, and to not dismiss uncomfortable possibilities out of hand. The story of 3IATLAS is a book with the final chapter yet to be written, and that chapter is unfolding right now. As the comet moves away from the Sun, through the remainder of November and all of December 2025, it enters the most critical phase of observation. The intense heat of perihelion is fading. What happens next will be the single most important clue to its true nature. Astronomers around the world are watching, and there are three primary possibilities they are looking for, three potential endings to this act of the drama. The first possibility is that the comet will simply fade as expected. As the solar heating decreases, the sublimation of its ices will slow down, the brightness will drop, and 3IATLAS will gradually become a dim speck, disappearing back into the darkness from whence it came. This would be the normal scenario. It would strongly suggest that the outburst was indeed a temporary heat-driven event, and that the object is, for all its weirdness, a natural comet. This would be a relief to many scientists, a tidy end to a messy puzzle. The second possibility is that the activity continues, or even changes in character despite the decreasing heat. Imagine if the solar heating stripped away a section of that irradiated crust, exposing a pocket of some extremely volatile material deep inside the nucleus. This material could continue outgassing furiously even as the comet moves into colder regions of space. This would be a spectacular discovery, telling us that the internal composition of 3IATLAS is radically different from its surface, a layered, complex world unto itself. But there is a third possibility, one that few scientists are willing to say out loud, but which they are undoubtedly looking for. What if the behavior changes in a way that cannot be explained by solar heating at all? What if there is a pattern to its activity, pulses of brightness, changes in its spectral signature, that suggests internal processes are at play, independent of the Sun's influence? What if it adjusted its trajectory in a way that couldn't be explained by simple outgassing? That observation would be world-changing. It would be the single greatest anomaly in the history of astronomy. It would shift the debate from, is it a weird comet, to, what are we actually looking at? Jiang and Batams, the first to document the outburst, specifically noted that the post-perihelion evolution could be just as unusual as the pre-perihelion outburst. What did they mean by that? What are they expecting? Or perhaps, what are they worried they might find? The next few weeks hold the key. We are all waiting, watching, and holding our breath. Regardless of what we discover in the coming weeks, the passage of 3IATLAS has already changed us. It represents a watershed moment in human history. For the first time, we have the technological capacity, the James Webb Space Telescope, our network of space-based observatories, our powerful ground-based spectrographs, to detect, track, and analyze a visitor like this in real time, with this level of detail. 20 years ago, this would have been impossible. We are living in the golden age of interstellar object research. Every anomaly, every unexpected behavior is a gift. The explosive brightening, the missing dust tail, the irradiated crust, each is a clue, a piece of a puzzle that is reshaping our understanding of the galaxy. This object is a message in a bottle, tossed into the cosmic ocean billions of years ago, finally washing up on our shore. The message it carries is written in the language of physics and chemistry, and we are just now beginning to learn how to read it. If it turns out to be a natural object, it will teach us that the universe is far more diverse and complex than we ever imagined. It will force us to rewrite our theories on comet formation and the chemical makeup of other star systems. It will reveal how the harsh environment of interstellar space modifies and transforms objects over time. But if it leaves us with anomalies that cannot be explained by natural means, it will leave a legacy of a different kind. It will leave behind a profound and persistent question, a question that will echo through the halls of science for generations. The implications are staggering. Think about what it means if interstellar space is filled with billions of these objects, constantly drifting between the stars, cross-pollinating the galaxy with the chemical ingredients of distant worlds. The galaxy becomes a single, dynamic system, a vast ocean of potential where the building blocks of planets are endlessly redistributed. But then think about the implications if even a tiny fraction of 1% of those objects are something else. If, hidden among the silent natural wanderers, there are artifacts, probes, constructs. What would that mean for our understanding of life and intelligence in the universe? It would mean the evidence we've been searching for with our radio telescopes might not be a signal from a distant star, but a physical object flying right through our own backyard. In the end, the story of 3IATLAS is not just about a comet. It is about us. It's a mirror held up to our own curiosity, our own assumptions, and our own courage to face the unknown. The universe is speaking to us through these silent visitors. It is telling us that our models are incomplete, that our knowledge is a tiny island in a vast ocean of mystery, and that the most exciting discoveries are still ahead of us. This story offers a powerful lesson we can apply to our everyday lives. Be open to the anomalies in your own world. When something doesn't fit your expectations, don't dismiss it. Investigate it. Question your own assumptions with the same rigor that scientists are questioning their models of comets. Have the humility to admit when you don't know the answer, and the courage to follow the evidence wherever it leads, even if it takes you to uncomfortable places. Like 3IATLAS, we are all on a long journey that changes us, that builds a protective crust around us. The most important act of discovery is often not looking out at the stars, but looking inward, to understand what lies beneath our own irradiated shell. The interstellar visitor has arrived. It has performed its unexpected and spectacular display, and now it is departing. It is heading back into the darkness at over 100,000 miles per hour, carrying its secrets with it. What it leaves behind is not answers, but questions. And perhaps that is the greatest gift of all. I want to leave you with a couple of questions to think about. If you could know the definitive truth about 3IATLAS, what would you hope it is? A natural wonder that expands our understanding of the cosmos, or something else that rewrites our place in it entirely? And what anomaly in your own life deserves a closer, more curious look? Thank you for joining me on this incredible journey to the edge of our understanding. I hope it sparked a sense of wonder in you, as it has in me. And if you want to continue exploring the biggest questions and the most profound mysteries of our world and beyond, make sure you hit that subscribe button. There are many more journeys to come.